So the first of the 5 techniques is the definition of the reliability function R of P. The second of the techniques is the expected value of phi of x. The reason that this technique works is the definition of R of P, which is the probability that the system is up, is the same as the expected value of phi of x, and the reason for that is that phi of x is a Bernoulli random variable, so it is only in states 0 and 1, and for that Bernoulli distribution, the probability of a Bernoulli random variable being 1 is the same as its expected value. So here's an example of using the expected value technique. Find the system reliability of a parallel system of n components using the expectation technique. Now we use this expectation technique with the definition technique and got one formula, and if everything goes well, this should certainly match that same formula. So this time, when you start to find R of P, instead of putting the probability phi of x equals 1 from up here, you put in the expected value of phi of x. So this step right here has to do with the expectation technique being used. That will always be the first step when you use the expectation technique. Now, phi of x in the case of a parallel system is 1 minus the product of 1 minus the x sub i's. We had derived that long ago when we were looking at structure functions. You know that the expected value of 1 is just 1 because 1 is a constant. You also know that the expected value is a linear operator, so the negative can come outside of the expected value. And now you have the expected value of this product. Well, what allows you to say the product or the expected value of the product is the product of the expected value? That step right there leans on the independence assumption. Finally, the last step, the expected value of 1 is equal to 1, and the expected value of xi, again coming back to the Bernoulli distribution, that's just p sub I, so we get this same formula here that we got before when we used the definition technique. There are 2 parallel system imposters that are worth looking at just to make sure that when you see you have a parallel system, you're thinking about the right type of system. The first parallel system, which is not a true parallel system, is called a standby system. In this particular case, not all of the components function at the same time. Components are switched from standby components to failure. So basically what you have here is you have a switch. We'll put an S by the switch, and then you have components 1 through n here. And so what happens is component 1 gets switched on, and then when it fails, if you have a perfect switch that works with reliability 1, it'll switch to component 2 all the way up to switch to component n. Now, that's not a bad system, and in fact that system has higher reliability than the true parallel system, but it is not a system which uses the formula which we derived on the previous page. What are a couple examples of a standby system? The first is when you bring spare pencils to an exam, that's a standby system. Unless you're ambidextrous, you can't use 2 at the same time, so you're only using 1 at a time, and you are the switch because once a pencil breaks, you just switch to another. Another one is keeping a spare tire in the trunk of a car. Now that one's a little bit more complicated because you have 4 tires that are working at one time, and then the 5th gets switched in if you get a flat tire. Example 3 sometimes shows up in hospital emergency rooms, but certainly in an intensive care unit, you might have 3 power sources. The first is the utility company, and when the power goes out with the utility company, there's a switch that puts in a backup generator. If the backup generator fails, then you have batteries. And so in a critical situation like an intensive care unit, the local municipality may require that there are 3 different power sources. Another imposter to a parallel system is called a shared parallel or a shared load system. All of the components are online, just like in a true parallel system, but the component reliabilities change when one component fails. So example 1 here are the lug nuts on an automobile tire. Let's say these are the 5 lug nuts on an automobile tire. Well, when one of those lug nuts comes off, you've got 4 remaining functioning lug nuts. However, those 4 remaining lug nuts are under a higher load because the one has fallen off. And that's considered a shared load system. That, by the way, has a lower reliability than a true parallel system. Another example is spokes on a bicycle tire. If one spoke goes out, that puts more of a load on the remaining spokes. So the story for a true parallel system is as follows. All of the components are online. They are all subject to failure at the same time, and a failure does not in any way alter the reliabilities of the surviving components. So the formula that we derived on the previous page applies to a true parallel system and not to either of these imposters.